dou t. And then we looked at what happens if we have a time varying magnetic field. We have seen that the time varying magnetic field will induce the electric field, and this induced electric field can be responsible for the current flowing in a loop if the loop is within the vicinity of the electric field. And if you open it, then you will see the EMF. And as I told you, the best way to find the terminals of the EMF is just put a resistor, and then from the resistor you find. So the current entering the resistor will be the positive terminal, and leaving the resistor will be the negative terminal. And therefore, EMF is nothing but you can get it from these two, which is basically coming from the Faraday's law. And then we looked at the three types of EMF. First is transformer, where you will get it because of only time varying magnetic field, but stationary stationary loop. Then you have motional, where your loop is moving, but your magnetic field can be static. And the third is both transformer and motional, where both your loop can also be time varying, whereas your magnetic field can also be time varying. And if you look at our previous example that we did, this example where we got the electric field in the region B, rho is less than B in that region. Now what we are doing is we are now trying to find what is this EMF, what is this EMF produced. So if I put a voltmeter here, what I will read. So this is what we are now trying to do. So now I'm now showing you guys both the methods, because just now we have seen that the EMF can be calculated either from closed line integration or from the surface integration. So we will use both the methods, and we will see that you will get the same answer. So first we will use the closed line integral. So now in the closed line integral, what I need to do here, I need to integrate over this closed line. And remember, for terminals, I have already told we always go from the negative terminal to the positive terminal. So now if I find the closed line integral over this one, or the closed line integral over this one, let's see what is the EM. So first what I will do, I will find E. So therefore E we already found here. So I'm taking the E from here, which is rho omega B naught sine omega t over 2 A phi. So that is my E A phi dot product with the line integration. Now in cylindrical coordinates, this line integration in cylindrical coordinates, this line integration, because our Z is coming out of the, this is my Z is coming out of the screen. So this is my A phi direction. So therefore, if you want to do a line integration over the A phi direction, then you will see that it will be A d phi A phi. Okay, A d phi A phi. So this is the line integration. Now, if you see, we are doing the integration over d phi. So what will be the units of d phi? Because d phi will be, excuse me, because d phi will be, so if this is my Z, so if this is my Y, and if this is my X, so my d phi will be the complete ring. That means my phi angle should go from here and return back to the same. So it will take the full complete limits, which is 0 to 2 pi. So that's why if you see here, we are taking the complete limits from 0 to 2 pi. And then if you see here, there is a term. See, because the integration is with respect to d phi, but we do have a term rho here. So therefore, for this integration, the rho will become constant. And what will be that constant value? That constant value will be, this value, which will be the radius of the ring. And the radius of the ring is your A. Okay, the radius of the ring is your A. See, it's of radius A. And then if you do this integration, then you will see that it is pi A square omega B naught sine omega t. Okay, because you can see there is no There is no d phi term here. So this is independent of d phi. So you can straight away take it out. And then what will be the area of this ring, which is nothing but pi a square. So this is the EMF that we got with method 1, that is using the closed line integral E bar dot dl. Now, how do we find method 2? Yes. So here it is minus integral over S dou B bar over d dou T dot ds. So first take B. So what is my B value? If you see here, this is my B value, B naught cosine omega t. And then first find its time derivative. So what is the time derivative of this one? The time derivative of this one is this one, which is minus omega B naught sine omega t az. And now we have to integrate over the surface. Now what will be the surface? Again, we will follow the Stokes theorem. So that surface is nothing but the surface which is enclosed by this closed loop or the closed thing, this surface. And we will follow the Stokes theorem. Since we did the integration from the negative to the positive, that is in the anti-clockwise direction. So therefore, the normal that I have to use for this surface, red color surface, is the thumb direction. So thumb direction. So I have to use plus AZ. So plus AZ will be the normal to my elemental surface ds. And what will be this elemental surface? Again, from the cylindrical coordinates, we can get that elemental surface, which is rho d phi, and AZ will be positive. Okay, because from the Stokes theorem. So your line integration and your normal to your surface, according to the Stokes theorem, it should be consistent according to the right hand. That's one. And then here you are doing the integration with respect to rho and with respect to phi. Again, phi will take the complete limit from 0 to 2 pi, and rho is the radius. So that's why it will take from 0 to a. And when you solve it, you are seeing that you are getting the same answer. See? So with this, we can appreciate that both the expressions will give me the same EMF value. Now, out of these two methods, which method is easier for us? It depends on your problem. But mostly, which method would be most easier? Yes, Mr. Ahmad Al-Ghamdi, can you tell me which method do you think will be the most easiest one?
Yes, can you repeat?
So should I use method 1 or should I use method 2 to find EMF? Which method would be most easier? Just now we did both. We did method 1 and we did method 2. Which method would be more easier? Which one do you think
method 2
most easier?
Yes, method 2.
Method 2. May I know why?
I think it's shorter, so we can do calculation.
Okay, it is shorter because we do not require to find the induced EMF. Because in this expression, if we want to use, first we need to find induced EMF and then apply the line integration. But here you can skip that step of finding the induced not induced EMF, induced electric field. So in this step, we need to find the induced electric field and then do the closed line integration. But here we can skip the step of induced electric field finding. So we can directly use the magnetic flux density, and from there we can find the EMF. So second method is mostly shorter. Okay. Now this is one more example of the EMF, but this example I'm leaving it to you guys, so you can do it at your home. Okay. So now let's go to the lecture 21. So now in lecture 21, we are now looking at the second type of EMF, which is the motional EMF. So in motional EMF, it will be produced, as we have just now, brief, that a time varying loop in a static electric field will produce the motional EMF. Now, to find the motional EMF, we will just go through some simple arguments. So if you see here, so what is the simple argument? I am now borrowing the magnetic force expression. So this is the magnetic force expression. And then from the magnetic force expression, which is Q times U cross B, I'm finding the induced motional electric field. How? See, Fm when I divide by Q, so magnetic force, if I normalize to the charge, what I am seeing is I'm seeing EM, and this EM is called as induced motional electric field. So I'm borrowing the same idea that I did it in statics. So the static force divided by the charge is, we say it as static electric field. Here, magnetic force divided by the charge will give me the induced motional electric field. It is induced because this magnetic force is being given by, experienced by this B, which is a time variable. And therefore, the motional electric field can be written as E bar M is just U cross B. And that is the reason you will have the motional EMF. So if someone is moving in a magnetic field and it is time varying, then that will generate a motional electric field. If B is time independent, doesn't matter, still it will generate. If B is time dependent, still it will generate. Time dependent, here you will have both. You will have this one as well as the previous one, which is the transform. So this is called as the induced motional electric field. And then how can I get the EMF expression for this one? We will argue along the same lines as we have argued for our Faraday's law. So if you see, what I'm doing here is I'm just, cross producting with my del operator. So del cross EM is equal to del cross U cross B. Okay. And then what I am saying is I am now comparing this. Excuse me. I am now comparing this with our previous lecture expression, which is this one, the first starting expression that we have, this one. Okay, so here I got del cross E is minus dou B bar over dou T, and here I get del cross EM is something right hand side. And therefore, if I do the closed line integration of this one, I will get the closed line integration of this one. Okay. So I am comparing this with my previous expression. And from there, I can say that the motional EMF is nothing but if this is a curl of EM, because in the previous case, we also got the curl of EM. This one, see, curl of E. So left-hand side is the curl of E. Here also the left-hand side is curl of now EM. And with this curl of E, I got EMF value as closed line integral E bar dot dl. So here also I will get closed line integral EM bar dot dl. And now the right hand side is dou B bar over dou T. So dou B bar over dou T. But here you have, or we are not looking at the right hand side. So this is closed line integral em dot dl. And what is my em? We are just substituting em. Em is u cross b, which is u cross b dot dl. So this is our expression. So we are just comparing the left hand side, not the right hand side. So the expression is the EMF is equal to closed line integral u bar dot p bar. So this is the motional EMF. Now, if you let your B become time varying, then if you see here, your total EMF will be the transformer as well as motion. So your transformer EMF is this one. So minus integral over S dou B bar over dou T dot ds, either this, or you can also use the closed line integral E bar dot dl. You can use any one of them. So we are using this one because this is most commonly used. Reason, it will be easier. You do not need to find the induced electric field and then find the closed line integral. So therefore this one. And motional, just now we have seen it. Just by a simple argument, it is closed line integral u bar cross b bar. So both will give me the EMF, and that is called as the transformer and motional EMF. So in this case, your del cross E, this is from the transformer, and this is from the motion, which we have just now seen. So here, del cross E is del cross of U cross B, and from the Faraday's law, del cross E is minus dou B bar over dou T. So therefore, the total induced electric field is because of this and this. So this is the total induced electric field. So it is coming from this right hand side, which is this one, and this right hand side, which is this. Okay. So this is the total induced electric field or the EMF expression. Now let's look at it. Let's look at one example. So this is a very good example, and we will go through this example. And this is the example of the motional EMF. Okay, it's the example of the motional EMF. So this is given to you, and we need to find the EMF which is induced here. Okay, and the terminals of the EMF is already given to us. So we are not finding the terminals by ourselves. When terminals are not given to us, then as I told you, you can put a resistor and you can find the positive and the negative terminals of your EMF. But here it is already given, so we don't need to worry. So now, how is this circuit? So this is the circuit where you have, these are conducting rails. So it is made up of conductors. And then you have a conducting brush, so which is also made up of wires, thin wires of conductors. And this rod, you are allowing this rod at time t is equal to 0. So this is your time t is equal to 0. You are allowing this brush to move over this conducting rail. And this complete, thing is under the influence of a uniform magnetic field B, which is B naught times AC. And this conducting, this rod with your conducting brush is now moving, and it is moving with a uniform velocity of u naught in the AX direction. So if it starts moving from here and it will start moving in this direction, then we will see that there will be an EMF induced, because this EMF is coming from this small conducting loop, and this conducting loop is becoming time varying. because at time t is equal to 0, it is this, it's here, but at time some value, it is here. So therefore, it is a time varying loop, and that's why you will see the EMF. Now, how to go and look at, solve it. So EMF is now coming purely from the motional because there is no transformer. Now, so it is integral over L U cross B. So U cross B. So we need to cross product U and B. So it is this one. So U naught AX cross B naught AZ. So this will be equal to U naught B naught. What is AX cross AZ? Minus AY. Okay. It is minus AY. So this we know, this is the cross product. Now we need to do the line integration of this over this 4 lines because the closed loop is made up of this 4 lines. 1, 2, 3, 4. So let's start. So first, if we do the integration over this line, then what has happened? So the integration over line 1 will be 0. Why? Because this is your starting point, and therefore as U is equal to 0, that is at time t is equal to 0. Then as you move, then you will have 2 and 4. So now what will be the dot product of U cross B and DL? Because this is this DL. So this DL, its direction is along AX, right? So this DL will be, so what will be the DL of this one? It will be DX AX. And the direction of this one will also be in the minus AX direction, doesn't matter, DX AX. But it is perpendicular to this. It is perpendicular to U cross B. So therefore, AX dot product with AY or AX dot product with AY will be 0. So therefore, there will be no contributions from 2 and 4 since the dot product is 0. Or I would say the DL is perpendicular to U cross B. That's all. So therefore, the only contribution comes is from this 3. And if you put, so you will get this dot. So for 3, so what is your dy? Your dy is your dy AY. And how we are doing the line integration? Remember, we also always need to go from negative terminal of our EMF to the positive terminal. So that's why if you see, we are going in the anti-clockwise direction. So in the anti-clockwise direction, the line integration should be in this manner. So that's why for this one, it is dy AY, not minus dy AY, because my y is in this direction. And then if you say complete this, you will get this one, minus U0 B0 AY dot dy AY. And what are the integrations of your dy? It is from 0 to h, because this height is h. And I'm not taking the direct. So this is your 0 to h. So 0 to h, and this is your answer. This is the EMF that you will see. Here, if you put a voltmeter, that it will be minus U naught B naught H. So if you put your B naught, which is a constant, H, which is a constant, and U naught, which is a constant, then you will see a negative constant voltage of this value. Okay, so this is called as the EMF, which you are seeing it on your voltmeter if you put it here, because of the movement of this rod with a velocity and in the uniform magnetic field. Okay, now The next question is, we want to repeat the same, but now my magnetic field is time varying. See, my magnetic field B bar is time varying. Now it is B naught sine omega t Az. It is now no longer B naught Az. So in this case, what will happen? Yes, in this case, what will happen? Yes, Mr. Nawaf, can you tell me? So what will happen now? If I change my magnetic field from uniform to time varying? Mr.
Yes.
Yes, what will happen?
The EMF will change also.
The EMF will change, but now the EMF will be made up of which two EMFs? Yes, which two?
I'm not sure actually.
Mr. Nawaf, you have, you have to pay attention. See, as I have already told you that if we see here, if you have B, which is static means uniform. If you have static, then the EMF will be only because of motion, only because of, so let's take this, only because of the movement of this rod. This is static. Now, if I make this be time dependent, then as we have seen here, your EMF will now have two components. You will have motional because of that, rod moving, and it is under now the time varying magnetic field. So still you will have the motional EMF, but you will also have transformer EMF. And the transformer EMF is because of the time varying magnetic field. Okay, so you will have both. If you see here, you will have both the transformer EMF and the motional. Okay, so the transformer EMF, find the time derivative of this. So it is B naught omega cosine omega t Az. Now what will be the ds here? Ds is nothing but the area. Ds is nothing but the area or the surface which is covered by your closed loop. It is the, and what is your loop? This is your loop. Okay, and you are going in this direction. So according to the right hand rule, the unit vector that I should take for this closed surface should be coming out, which will be the Z1. So if we use that, then if you see here, it is dx dy az, because the surface is coming out, dx dy az, and this is dou b bar over the surface. And this is u cross b. We just now did it. We did it for the uniform case, but now here you can just substitute, instead of b naught z, you can substitute b naught sine omega t is. And then you can complete this. So your y is equal to 0 to h. And therefore, since it is only with dy, so u naught b naught sine omega t is a constant which comes out, and therefore you will get h. And now here, if you dot product this is dx dy. So therefore, b naught omega cosine omega t will come out, and only dx dy. Now we need the limits of dx and dy. So dy is straightforward. It is from 0 to h. Okay. See here, your y is straightforward. It is from 0 to h. Now, how do you find the unit of x? So x is starting from 0. From 0 to where? This you can simply do it with the following argument. So this is my velocity, right? So this is my velocity. So dx over dt, because it is going in the x direction, dx over dt is u naught. So therefore x is what? U naught over t. So using this argument, we can get the x. And that's why I wrote here, it is u naught t, because after time t, you will see it somewhere here. And this distance will be nothing but the speed multiplied by the velocity multiplied by the time. So u naught t. So that's why here you have x is equal to 0 to u naught of t. And now if you do the integration, you will get this 2 terms. So now it is no longer 1 term, it is 2 terms. And this is from the transformer EMF and this is from the motional. So this is a very good example where, you know, we are coming slowly step by step. We looked at the transformer EMF. We looked at both the expressions from which you can get transformer EMF, and we saw that both the expressions will give us the same answer. Then we went to the motional EMF, and then after the motional EMF, we went to both an example where we have both transformer and motional EMF. And we saw that indeed you are seeing 2 expressions coming from the transformer and from the motional. Now what we are going to do is, now since it is very long equation, right guys? If you see here, this is a very long equation. So now what Faraday did is Faraday also gave us a very simplified equation for this EMF rather than remembering all these things. And Faraday told us that EMF is simply minus d psi over dt. This is when your loop has only 1 term. When your loop has n terms, then just multiply it by n. It's a simple superposition multiplied by n. So it is minus n d psi over d. This is the very simple expression which is also called as Faraday's law, because this is again coming from the same Faraday law, but it is very simplified. Okay. And it states that the EMF in the closed circuit is nothing but the negative time rate of change of the magnetic flux linkage, because it is n times phi. So that is the magnetic flux linkage. So now can we do the following? You know, let's now use this expression, because in our previous example we used this expression, right? Now let's use this expression to see whether we will get the same answer, where for this part where we had only motional EMF, and for this part where we had both transformer and motional EMF. And let's see whether this simplified expression is indeed taking into consideration this big complicated expression. So let's do it. So now for 1, let's see for 1. So we need to find psi, right? We need to find the flux. So you will find the flux which is passing through this loop. You'll find the flux passing through this loop. Okay, so this is my loop, and we need to find the flux which is passing through this loop. Maybe I should not use this one. Let me use a different color. So I need to find the flux passing through this loop. So to find the flux passing through this loop, I need to first know the area of this loop. So first I will find the area of this loop, and if I dot product ds and this b which is coming out towards us, this is what we need to find. So psi will be equal to integral over s b bar dot ds bar. So which is integral over s b naught, okay, b naught az dot, what is ds here? What is ds here? Again, the ds will be defined by the direction of the negative and the positive terminal with the right hand rule. So again, in this case, your ds should be the positive z coming towards you. If you curl your hands, curl your 4 fingers from negative to positive, then thumb will be showing the direction which is positive z direction. So it is dx dy az. And therefore this is equal to how much? What is your dx and dy? So B naught dx dy. So what is your dx and dy? So x is now again from 0 to u naught of t, which we have just now found it, and y is from 0 to h. So you will see that it is B naught times u naught of t times h. Okay, u naught of t times h. Now let's go back to the page. So let me erase everything. So let's go back to the page where it is. It is here. Okay. So now I got my psi. So which I have just now told you. This is my psi. I just now derived it. Now put it in this expression. So it is minus d psi over dt. So this is minus P naught u naught h. And is this the same expression that we got here? See? Yes, minus u naught b naught h. So therefore, rather than using such this expression of u cross b dot dl closed line integral, you can straight away find the flux, and from the flux you can find the EM. Now, can we now do it for our second example, which is here? So now B is B naught sine omega t. So let us do the following. Again, your flux will be B naught sine omega t times u naught of t times h. Okay, using the same procedure that I told just now. And if you find the EMF, you will see that your EMF is minus d psi over dt. So here with respect to t, so you have two terms. So therefore you have to use the proper say differentiation of ub or d over dt of say at and bt. The formula that we have. So based on that, so it is first. And sorry, this is the derivative of first, keeping the second as it is, minus keeping the first as it is, derivative of second. Okay. And then if you simplify, this is the answer. And if you look at the answer, and then let's compare this answer with what we got here. It's the same. It's the same. So what is the important conclusion here? The important conclusion is this simplified expression of EMF automatically takes into consideration both the transformer EMF and motional EMF. Automatically take into consideration both transformer and motion. And if you don't have transformer EMF, you have only motional EMF, still the expression is varied because we have seen here. So therefore, the end message is we don't need to worry whether your problem has only transformer EMF or motional EMF, so that you need to look for the transformer EMF expression or motional EMF expression and then use. This simplified expression of EMF is minus n d psi over dt automatically takes into consideration any type of EMF your problem has. Okay, so now you can appreciate about this expression, although it is very simple, but how important it is, and how it takes into consideration both these complicated expressions. Okay, so now from now onwards we can use this expression, but remember, you have to look at the problem and then you have to decide what to do and what expression to use and what expression not to use. Okay, so I think we will just this is an expression, this is an example which I am now leaving it to you, so you can look at this example at your home. Let's take this example, and and in this example we will use both methods, that is the long method and the short method from finding psi and then from finding EMF in this method. We will again check. So it is saying that you need to develop an expression for the current induced in the circuit shown below by two methods. And it says that this edge of my loop coincides here at the x-axis at time t is equal to 0, and then it starts moving. And my magnetic field is magnetic flux density is B naught cos beta x times AZ. And this loop is moving with a uniform velocity u naught ax. So, and it is of height h and width w. So first, what kind of EMF do you think this example will have? Yes, Mr. Thabit, can you tell me?
Yes, lecture.
Yes. So what kind of EMF you are expecting, or what kind of EMF you are expecting in this loop? So is
I'm
it
not sure.
transformer EMF, motional EMF, or both? How do you find this, Thabit? You can find this by looking at B value. Looking at B and tell me. See, the loop is already moving, right? So definitely you will have motional EMF. Now look at B value and then tell me whether it will be only motional or motional plus transformer.
Is it both?
Yeah, no, it's not both. See, how do you identify whether it is both? When your B is time varying. Because if your B is time varying, then yes, because of the movement of the loop, you will have the motional EMF. And because of the time varying, you will have the transformer EMF. But is this time varying?
No.
No, there is no T here. So it's not time varying.
Yeah.
Yeah, it's varying with respect to X. It's a spatial coordinate, not to worry, but it is not varying with time. That's why you will have only motional EMF here. Okay. So,
Okay. Great.
okay. So now, because I don't have any time component, so therefore it's only motional EMF. So it is closed line integral u bar cross b bar dot dl. Okay. And my loop direction is already given to us, which is this direction. So we will follow that. So therefore my u cross b, first you need to find u cross b. So my u cross b is minus this times a bar. Now again, we need to go and do the individual line integration of this 4 lines. 1, 2, 3, 4. So 1, 2, 3, 4. Again, from our experience just now, we know that 2 and 4 contribution will be 0, because here my dl vector will be perpendicular to u cross b. So that's why 2 and 4 will vanish. Now you will have 1 and 3. You will have 1 and 3. Now, why you will have 1 and 3? It is from this 1 and it is from this 2. So if you see here, so this is my, this one, my 1. So where I have integral 0 to h, u cross b, and it is minus ay dy. So why it is minus ay dy? Look at the direction. Oh, it's times. Give me a minute. So you look at the direction. The direction is going down. So that's why it is minus ay dy. And I'm not taking into consideration the direction in the limit, in the limits of the integration. That's why. And this is for 4. And now the thing is, when it is moving, what if you see here, you have an x here. See, you have an x here and you have an x here. That's why this is not canceling to 0. You have an x here, because in the previous case, this first was becoming 0, but here it will not, because you have an x here. And what is that x? So the x will take u naught of t, and here x will take u naught of t plus w. So because this is also moving, see, this line is also moving, this line is also moving. And there is a constant difference between them, which is the length W. So if this is moving with a velocity with u naught of t at an instant time t, then this will be u naught of t plus W. And therefore, that if you substitute here, you will get this answer. And you can now do it with your psi, and you will see that you will get the same answer. Okay, so therefore you can use any of this method, but finding the psi is much easier. Okay, so I think, guys, we will stop here. It's time. And in the next class, we will quickly review this, and then we will move to the next part. And there I can take your questions.